Good afternoon, everyone. Good morning to our visitor from Austria. My name is Jarrod Leak. I'm the CEO of the Australian Alliance for Energy Productivity, or A2EP. I'd like to welcome you to our latest webinar on industrial process heating. May I start this webinar by acknowledging the traditional owners of where I am living and broadcasting from in the northern suburbs of Sydney, that being the Darramurrugal people, and I pay my respects to their elders past, present and emerging. If you would like to acknowledge the traditional owners of where you are today, feel free to put that in the chat box. Good. So today we are brought to you by our members. A2EP is a not-for-profit organisation funded by these fabulous members, and these members share our mission to double Australia's energy productivity. In short, A2EP helps business pursue a cleaner and more successful future by producing more with less. We explore world's best practice and connect our stakeholders and members together, and we advocate for programs and policy that help our members increase energy productivity, increase jobs, all towards a zero emissions future. Today we've got a webinar for about an hour and a half. And we'll be starting off with a presentation on a high temperature heat pump. I'll have an introduction from Dr. Veronika Wilk in just a moment on that one. We also have, joining us today is Jon Fettes from Regenerate Engineering, along with Michael Belstead from -40. They'll be giving us a summary of the latest feasibility study results for the 3 Ravens microbrewery. After that, we're going to have a product specialist from Simble Group, Bill McGhie, is going to give us a rundown on metering and monitoring for industrial heat pumps. As we know, metering and monitoring being enabler number 2, I'd say, after enabler number 1 of a decarbonisation commitment, but probably enabler number 2 in terms of getting energy productivity projects happening. Metering and monitoring being so essential, we'll try and include that in all of our webinars in future. So thanks for Bill joining us today. After that, we'll have a quick summary from myself on the arena process heating studies that we've been doing over the last year or so, a wrap up of those, and also an introduction of our heat pump selection guide and calculation tool. I'll run you through that, and after that, the tool will be available for people to get a copy from myself later. So without further ado, let me move on to our first speaker. Today we have Dr. Veronika Wilk joining us from the Austrian Institute of Technology. Veronika has been working with heat pump demonstration projects over the last few years, and specifically in high temperature heat pumps. Now, in the past, we've talked about high temperature heat pumps being, say, greater than 65 degrees, maybe less than 95 degrees. And certainly with the studies that we've done with ARENA, very quickly see that can do a reasonable chunk of process heating demand out there. But there is a very large amount of heating required from 100 degrees to, say, 160 degrees. And it's great to see that heat pumps are getting into that envelope. And we're starting to see that demonstration plants and more projects happening in that space. And so with today, Veronika is going to take us through DryFiciency. Veronika will give us a quick background of that organisation and the projects that they're working with and the demonstrations. And we'll see about the developments that are happening there. So with that, Veronika, I'll stop sharing and we'll get you sharing your screen and we'll see some more about what's happening with DryFiciency and heat pumps in Europe.
Okay, can you see my screen now?
Sure can. That's come through perfectly. Thank you.
Okay, perfect. So thank you very much for the invitation. It's a great pleasure for me to join you today. And I will give you an overview on the DryFiciency project, where we develop high temperature heat pumps for drying. I work for the Austrian Institute of Technology. It's a research and technology organization based in Austria, in Vienna. And we work on all the topics that will be relevant for the future, for the Austrian infrastructure, but also not only for Austria, but for all other parts of the world, hopefully. And our special focus are high temperature heat pumps, where we have already quite a long history in doing research. And now we have this DryFiciency project up and running for about 5 years now. It's a Horizon 2020 project funded by the EU, where we set up 3 demonstrators to test this technology in an industrial environment. And on this slide, you also see our project partners. So it's a small but a very effective group of component manufacturers, system specialists, end users, and also our dissemination partners. And yeah, so I will move to the next slide here. And in the course of the project, we have set up 3 demonstrators that are shown on these pictures here. They are integrated in different drying processes, and we decided to tackle drying processes because you find them in a number of industries. Whenever you want to evaporate water, drying is needed, and it's also very energy intensive to overcome the evaporation energy of the water. And
Veronika, did you go to the next slide there? We're still seeing the
yes.
introduction slide.
Okay. So can you see it now? Because it's I will just share it again, and maybe that will help. So how about now?
Just waiting for that. We're coming a few miles. And if we do have problems, I've got a copy of the presentation. I can always run through that, and we can do that.
Yeah.
Can't see.
I
maybe let's
switch to the presentation window.
Yeah, no, that's not. It says it's screen sharing, but it's not coming through there. Before.
Okay. So, well, if you can show the slides, I'll just stop mine.
Yeah, let's do that. I've got it in PDF, but that should still be fine. I'll just sort of scroll.
Yeah,
through.
it's just it should be the same.
Yeah, indeed. Very good. So hopefully everyone can see that coming through now.
Yes, I can see it.
There we go. I'll scroll through.
Yeah. If you press Control and L, we'll get it to full screen.
All right. Thank you. Okay. Go for it.
Okay. Yeah. So then we go to the second slide, please. Yes. So here we have our 3 demonstrators. So we work on different kinds of high temperature heat pumps within the project. And we have built 2 closed loop heat pumps that are used for air drying processes, and an open loop heat pump which is used for steam drying. And so from left to right, we have the red container. It's a closed loop heat pump located at Wienerberger in Austria. Wienerberger is the world's largest brick producer. And we have integrated the heat pump in the brick drying process. In the middle, we have the gray container, which is the second closed loop heat pump. It's located at Agrana, an Austrian company producing products from potatoes, corn, and wheat. So it's a food company. And on the right, we have the open loop heat pump for steam drying. This is the research work of SINTEF. SINTEF is a research and technology organization based in Norway. And their focus is on mechanical vapor recompression systems. And this kind of system is integrated into a sludge drying process that is located in Drammen in Norway. And the aim of that development is to reach 160 degrees C. And yeah, so let's move to the next slide. Could you please move the slide?
Yeah, I did that about 5-10 seconds ago. I think we've got a good delay there coming to you, but
okay.
I'll try and anticipate the next slide change.
Oh, okay, yeah. Yeah, we will manage. Yeah, so I will just fill the gap and tell you just a little bit of more information. So so as I've said, we have these two different systems because we think that we can cover all types of drying processes with that heat pumps. And it's also very interesting to get an insight into two different types of technologies and see their applications. Air drying processes are very common, so using hot air to remove water. But steam drying is maybe not so well known. So there the products are dried in a steam atmosphere. So the water is evaporated and is mixed with the steam that is fed into the dryer. So you start with a stream of high pressure, high temperature steam, and then it's mixed with the water that's evaporated from the product. And you get the largest stream of low pressure, low temperature stream. And basically with the mechanical vapor recompression, you can just reintegrate that steam. So, did you see a change in the slides already?
Yes, I'm now on the open loop heat pump.
Oh, okay, because they didn't change for me. That was a bit confusing.
Yeah, it's got quite a delay.
Okay, so the delay is just for me. So then I can move my own slides and then I would just tell you what I see and then we can just synchronize that somehow.
Yeah, let's do that.
So you see the open loop heat pump right now.
That's right.
Yeah, so, okay. So the main part of the open loop heat pump is that steam turbo compressor that is the development of Rodrex. And it's done a turbocharger technology from the automotive sector. And the aim is here to have a very compact design that enables a cost-effective product. And it's also an oil-free compression design, which is very useful because then you don't have to worry about the compatibility of the oil in the product. And it's also useful for the food industry to have a oil-free system so that the steam can get in contact with the product also. On the right side, you see the condenser. So the steam that is coming from the compressor is used to heat the process steam that is moved in a circle. So we condense one part to heat the other part. And the aim is also to reach a temperature lift of 50 to 60 K in 2 stages of compression. Yeah, so could you please go back to your previous slide because yeah, the other way for the closed loop heat pump.
Yes.
So now it's also moving for me, so we are synchronized.
Good. Back in action.
So the closed loop heat pump is sketched here. It's like, so the layout is quite similar to like a traditional heat pump for household or commercial applications, but we moved that cycle to a higher temperature. So we have an industrial waste heat source at temperatures around 80 degrees C that we use to evaporate the refrigerant. And as a refrigerant, we use a synthetic fluid produced by Chemours. It's Option MZ or R1336 MZZZ. And it's not flammable, it's not explosive and non-toxic, and also has a low GWP value. And it was especially developed for high temperature applications. And at AIT, we were also the first to test this new material in the lab, which was also one of the basics to start this EU project afterwards. And another important component of the closed loop heat pump is again the compressor. We have 2 different types of compressors for the 2 demonstrators. So it's on the one hand a screw compressor produced by Kühlmaschinenbau, a refrigerant component manufacturer based in Germany. And they took their screw compressor series for industrial application and moved it to a high temperature application. So they checked every part if it's compatible with the new conditions and built 4 new compressors that are used within the DryFiciency project. And the second compressor technology that we are looking in is a piston compressor. It has been developed and produced by Viking Heat Engines, that is now Heat and AS, a Norwegian-based company. Also having a history in ORC processes, and they adapted their OSC module to heat pump operation, also tackling high heat supply temperatures. And the closed loop heat pump requires lubrication for the compressors. And we also have a lubrication specialist within our consortium. It's Fuchs, also based in Germany. And they developed a lubricant that is compatible with the refrigerant and the high temperatures. And there it's, for that question, it's important to ensure thermal and chemical stability so that the fluids don't get too reactive with each other and start degrading too quickly. And yeah, on the left we have the condenser. This is where we supply the heat to the industrial process. And yeah, the aim is to reach 160 degrees C. And to close the cycle, we have the expansion valve to reduce the pressure again. So these heat pumps are located within an industrial process, but we have constructed a very nice integration infrastructure that allows us to test different conditions and to operate the heat pump as a part of the process, but not being essential for the operation of the process. So it's really a demonstration and test facility where we can try different conditions. So now I would like to move to the slide about the starch drying. Yes. So here you see how we integrated the heat pump into the starch drying of Agrana. So it's a flow stream dryer where the wet product is fed as a solution into the dryer. It's dispersed there, and there's a stream of hot air coming in where the particles are dried and then trained within the dryer, and then the dry product is separated from the airstream, and the exhaust gas is leaving the dryer. So they use typically 200 tons per hour of drying air with an inlet temperature of 58 degrees C. And on the right side, we have the installations needed to heat up the drying air. So the first heat exchanger is using water coming from a hot water cycle. So it's the heat recovery system that they already have in place. So they collect waste heat from different other installations. So this water cycle has a temperature of 90 degrees C. It's used for preheating, and after the preheating step, the water cycle still has a temperature of 70, and the air is heated to approximately 88 degrees C. Then we have the heat pump, the heat exchanger for the heat pump, and then there's a heat exchanger that is using steam to ensure that the final drying temperature is reached. And as the heat source for our heat pump, we use that hot water cycle that still has 70 degrees after the heat exchanger. And the heat pump is connected to the drying air with an intermediate cycle. And this is just to ensure that we can test different temperatures, that we can also measure different temperatures in that water cycle to really have a nice balance on the heat pump and check all the operation conditions. And the heat pump demonstrator has a lower heating capacity than is needed to fully supply that drying process. So we have heating capacities of around about 400 kilowatt, and the whole system requires 4 megawatt of heat. So it's 10%, which is a good size for a research and demonstration object to learn from the real behavior, but not being excessive on costs and investment. So that's for the starch dryer. Maybe another word on the heat source. So a very interesting heat source for drying is, of course, the exhaust air, because there you have a lot of humidity that has been removed from the product. We also looked into that stream as the heat source, but as we have this high temperature, that heat recovery cycle available that has a higher temperature than the humid exhaust gas, it was more efficient to use the water cycle instead of the humid air. But to go on with waste heat integration, this is definitely an interesting heat source, and it's also very good for the use in a heat pump. So on the next slide, we have the brick drying process of Wienerberger. So we have here the two important process steps of brick fabrication. The lower part, we have the tunnel dryer. The wet product is coming in with 28% of moisture, and the bricks are moving on wagons through that tunnel dryer. And after the drying step, they have a residual moisture content of 2%, and this is necessary to prepare them for firing in the kiln. This is shown in the upper part. So they enter the kiln at 20 degrees C and they're heated to 1000 degrees C. And in the final part of the kiln, there's cooling air coming in, and then the product is leaving 50 degrees C. And both steps are energy intensive for brick production. And we integrated the heat pump into the drying process. So there we have, there's also a heat recovery system already in place. It's a thermal driven heat pump, making use of the waste heat from the kiln and also using the humid exhaust gas from the dryer. And with this thermal driven heat pump, a water cycle is heated to 90 degrees C, and this is transferring the heat into the tunnel dryer with that heat exchanger surfaces that are located within the tunnel. And in that sketch, you also have the temperature profile of the tunnel dryer. So we start at lower temperature and to reach higher temperatures in the final drying zone to really ensure to reach that final residual moisture content. And the air and the bricks are moving countercurrently. So the air is fed at the final end, moving through the dryer in a countercurrent flow. Our heat pump is also using that waste heat recovery cycle and is integrated. So the evaporator is integrated before the drying surface, the heat exchanger for drying within the tunnel. And there's a recirculation airstream taking air from the front part of the dryer and moving it to the final part of the dryer. And there typically a gas burner is installed to increase the temperature, and this is where we have integrated the heat pump to heat that recycled airstream. So let's move to the next one. Yeah, so I have compiled here some pictures from the construction and assembly phase. So we started with numerical simulations to determine how the heat pump should look like, to determine all the important boundary conditions for basic and detail engineering. And then we tendered the construction of the heat pump. So we have all the different components coming from our project partners, and then we tendered the assembly and construction. And those are some impressions from the work carried out there. And on the next slide, we have some impressions from process integration. So the heat pump located at Wienerberger was moved into the factory via the roof because it's a very densely constructed factory. And in the picture in the middle, you also see the process integration. So basically, there are 4 pipes to be connected. It's a bit more complex than that, but we have the heat source coming in and going out, and also the hot water that's provided from the heat pump coming in and out, also electrical connections and also connection to pressurized air. And the picture on the right was taken at our demonstration event. So this was the very first public event where we showed the heat pump to a group of visitors when we started operation. So on the next slide, yeah, we have the first operation results. So this is what we have measured and learned so far from the heat pump at Wienerberger. So we have operated the heat pump at different heat supply temperatures, and we successfully reached the 160 degrees C. And yeah, so I will talk you through that diagram. On the x-axis, we have the temperature lift. This is the temperature difference between the heat source and the heat sink. And on the y-axis, there we have the CUP. And the red squares are the results from the DryFiciency heat pump. And we have here the four main temperatures that we have tested, 120 up to 160. And the blue dots that are shown here in this diagram are taken from a rather recent publication They give an overview on high temperature heat pumps, on the market of high temperature heat pumps. They were compiled by Gordon Abergaus. I think he was already a presenter in your webinar series. So these blue dots are a representation of the current heat pump market. And then we compare them to the DryFiciency heat pump based on the temperature lift, because this is it's a sound comparison. And the gray line indicates the relationship of COP and temperature lift for an ideal heat pump reaching 50% of second law efficiency for heat sink temperature of 120. So this is just a rough indication to show the behavior of the closed loop heat pump. And the DryFiciency heat pump is among the more efficient examples, being in the upper third of the values here. And this also reflects that it was these are very satisfactory first operation results. And on the next slide, on the next slide, we see how the heat pump compares to a natural gas burner, because this is the fossil technology that we want to replace with that development. And those are values for Austria. So we calculated for our demo sites based on the operation data of the DryFiciency heat pump. And on the left side, we have the reduction in end energy and CO2 emission. And again, on the y-axis, there's the heat supply temperature ranging from 120 to 160. And the savings in end energy and CO2 emissions are above 65% for the highest heat supply temperature and go up to more than 80% for 120 degrees C. And on the right side, we have the energy costs based on average industrial energy prices in Austria. So the blue line is the current situation, reaching about 50% of energy cost reductions when supplying 120 degrees C, and having still 10% of energy cost reduction when the heat pump is operated in 160. And the red and the gray line give an impression of the future to come. So there we included a CO2 price, the red line with the current CO2 price of 24 euros per ton, and the gray line with an increased CO2 price of 50 euros per ton. Which is still not a very exaggerated CO2 price. So if we look at the highest heat supply temperature, there we see a strong influence of the CO2 price. So with the 50 euros per ton, we will get more than 30% of energy cost reduction. And this also shows the influence of this kind of policy for energy efficient technologies. So let's move to the next slide. Yeah, and here we have a comparison with other ways to supply heat. So it's again the COP diagram that we had before with the results for the DryFiciency heat pump. So and now we use that to compare it to other technologies. So as long as the COP is above the black threshold, energy cost reduction is possible in Austria. So the diagram that we've seen before is calculated with average values for Austrian industry. But you can use that diagram and see whether the ratio of electricity and natural gas price allows for cost reduction or not. And the two other lines that are given here, the blue one is an ideal electric heater, which basically has a COP of 1, and a typical natural gas burner with an efficiency of 90%. And as long as the COP is above those two lines, there are energy savings compared to these two technologies. So we still have still possible to move to higher heat supply temperatures and saving energy compared to a direct electric heater or compared to a natural gas burner. So I stopped a diagram of a temperature lift of 140 degrees we have a heat supply temperature of 90, so this corresponds to 230 degrees of heat supply temperature. So this is it's also maybe a glimpse into the future, what's still possible. So yeah, I'm already at the end of my presentation, and I have put here some important aspects. So we have successfully commissioned the DryFiciency heat pump at Wienerberger. We reached the 160 degrees C, which was basically, this was one important part of the project to show that those high heat supply temperatures are possible. We are very happy about the COP values that we have reached, and this also translates in significant CO2 and energy cost reductions compared to natural gas. We are convinced that demonstration projects are a very important step towards establishing new technologies in industry, because with this type of project, we can really show how these technologies behave in reality. And the technologies that are developed within DryFiciency are not just limited to drying processes, but they can also be used in other types of industries that require process heat up to 160 degrees C. This is, for example, the food industry. Different examples, so breweries, dairies, sugar production, for example, or the paper industry or the chemical industry. And on the last slide, I want to thank the DryFiciency team for the very good collaboration and effort. So it's not possible to do such a huge project without engaged and motivated colleagues. And there's another slide. And I want to take the opportunity to invite you all to the DryFiciency webinar series that is that will take place in April. It's also online, so you can also join from other parts of the world. And we will also have a final conference on the 6th of July where we will present all the important aspects of the project. So thank you very much, and I look forward to your questions.
Wonderful. Thank you so much, Veronika. That's really gives us a lot of hope there that further work can be done with these heat pumps. So it's great to see actual real demonstrations happening rather than just the lab scale that we've been hearing about the last year or two. Thank you so much. We did have a couple of questions there. We had one, just a quick one there from Michael Belstead about Viking heat engines. That you mentioned quickly that they've changed their name. Is that it's just called Heating AS? Is that correct?
It's Heaton AS.
Yeah.
It's the successor company.
Very good. Question here we have on the open cycle loop heat pump. Mentions a temperature rise of 50 to 60 degrees. With delivery temperature of 100 degrees. Does this mean in effect that returning condensate at 100 degrees can be lifted to 160 degrees steam? What is the waste heat source in this scenario? Air, water, waste heat from industry?
So the open loop is operating on steam only. So it's not the condensate that is lifted to 160, but the steam coming from the dryer that has a temperature of around about 100 degrees C, and then it's compressed in getting higher temperatures and pressures. The condensate so we also have the condenser in that layup, and it's just for transferring the heat of the stream that was compressed to the drying. The condensate can be used again for other processes.
Okay.
So for the open loop heat pump, the dryer is basically a part of the heat pump. So the dryer is the evaporator, so to say.
Yep. So the exhaust from the dryer being the evaporator, and then going around to the condenser to drive the fresh air coming into the dryer.
No, the open loop, there's no air. There's no air in the open loop drying system. It's just operated on steam. Also, the dryer is operated on steam.
Okay, good, thank you. And we'll send out the slides as well, and there'll be no doubt interrogation of going over those little process diagrams as well. Good. With regards to the brick drying, got a question here from Cameron Stanley from RMIT, asking about the tunnel dryer. What percentage of the energy is used in the tunnel dryer for the overall versus the overall brick, the energy for the overall brick making process? Have you got that sort of info?
I do, but I don't know it by heart. But I would estimate that to be around about half of the energy input to the process.
Mm-hmm. And I think you had shown something like a 70 or 80% reduction potential in the energy used in this step.
Yes. So the calculation we assessed the heat pump compared to a natural gas burner that delivers the same amount of heat. So for the brick factory where we have integrated the heat pump, that impact is not that big because it's just a small demonstration plant within the process. But for the full scale, this is what to be expected if we replace just that natural gas is currently used.
Very good, thank you. So that, you know, if you are talking about that sort of, if it's 30–40% reduction in energy, that's quite a step change for the brick making process. So I'm sure that'd be very welcome. Great. Thanks for the questions from the audience there, much appreciated. And Veronika, thanks for the presentation. I'm sure hopefully you'll stick around and we'll go through a few other little pump developments here in Australia for you.
I will, thank you.
And so with that, we'd like to hand over to Jon Fettes. Jon, if you'd like to share your screen, we'll bring that up. Jon is the Managing Director from Regenerate Engineering, and he's joined by Michael Belstead, the MD for -40. We're going to take us through the heat pump feasibility study and the results from that from the lovely Three Ravens craft brewery there down in Melbourne. Jon, I hand over to you and take us through it.
Okay, thank you. I hope you can hear me.
Sure can.
Excellent. Thanks, Jarrod and the awesome people at A2EP for giving me this opportunity. That's Murray, the brewer, by the way, and Brendan, the brewer, is also, I think, in attendance, along with Nathan, who's the general manager of Three Ravens. So, yeah, basically, breweries are all very similar in their energy processes. According to the entropy law, second law of thermodynamics, the chillers, like all chillers, produce more heat than cold, but very rarely is any of that heat actually used. And the actual process heating used is usually resistive, electric, or gas. But with a single cycle heat pump, we can improve all processes except the boil. And despite not being able to improve the boil, we can typically save 50% energy cost on the whole brewing process, and more if we add value, if we value add the process. Here's a representation of a single cycle CO2 chiller heat pump operating in transcritical mode. How does it work and what are the constraints? The heat source at one end is glycol, and the energy moves from the glycol to piping hot water at the other end. Temperature shown there is 95 degrees, but if you were to pressurize the system, you could potentially get up to 110 degrees. And this process, as you see there, can run indefinitely, at least until the cold storage tank, and to a lesser extent, the hot storage tank is full. If the feed from the bottom of the hot tank there becomes warm, the gas cooler will cool it and return the CO2 back to the compressor at a viable temperature for the cycle to continue. In practice, the gas cooler will operate most of the time. By adding a second heat exchanger at the hot end, we can value add the process and use this waste energy for an optional mid-temp heat service, such as space heating. So that's transcritical mode. This is subcritical mode. When we don't need to produce that hot, super hot water, the compressor can switch to subcritical mode and act simply as a chiller. And the heating COP is actually improved in that situation, but the overall system efficiency is reduced as the heat is wasted. But again, as a bit of a bonus, we can configure the system to intercept that heat and put it to good use for our space heating, or anything else for that matter. As you'll see, the COPC is higher in the winter due to the efficacy and the extent of the gas cooling, sorry. So Three Ravens, I met Three Ravens in 2019 through a Darabin Council-sponsored small audit program. It was immediately obvious that the pieces are all there for a heat pump upgrade, and Three Ravens management came along to Northlink Forum. They are like a food and fibre industry group, and a talk by Michael from -40. Michael's a natural refrigerant specialist here today. From this mini project, there's a suite of recommendations, including the single cycle heat pump idea, which they were very keen on. They were planning an upgrade anyway. They have a conscience, they want to reduce their greenhouse emissions. The solar upgrade resulted in significant energy cost and emissions reduction. And as you see from the real picture over here, not the one behind me, we did leave space for the gas cooler plant above the brewery. So we got approval to kick off the A2EP pre-feasibility study at a similar time as we heard a positive grant outcome, and so things got going. And it was only after the pre-feas was complete when we saw the super detailed interval data from the solar install. We found that there was hydraulic problems evidenced by the chiller's behavior. It was cycling on and off, even though there was a vast amount of heating to do in this particular, or cooling to do in this particular weekend. We'll touch on that in a couple of slides. So these are the screenshots of the model developed for the pre-feasibility and subsequently the full feasibility study for A2EP. It's the work of my colleague Rob Alexander. This is largely a reusable and replicable process, but for further projects, we'll be able to recreate and streamline the model. We had to understand the balance of heating and cooling, which is a mass and energy balance, and understand the totals of the energy for the various parts of the process. We had to do some batch calculations. And when we got back heat exchange designs from specialists, Alfa Laval and Teralba, we integrated the parameters into the model. As you'll see, Rob is a master of color coding and also version control. And we're up to version 13 of the spreadsheet. As noted before, there were things which precluded the integration of the new plant into the existing plant. Basically, we're not going to have a project unless we redesign the plant. The result was a complete hydraulic redesign as required for any increase in production, but more specifically to suit the peculiarities of CO2 refrigerant cycle, a cycle where the gas never actually condenses. This process was heavily informed by Michael from -40, and he'll be available for technical questions at the end. That's also -40's energy model at the end. Okay, so storage. So before I go through the storage system, I'd like to point out the importance of design for stratification, especially when you have batch processes. When you're setting up a facility, it's tempting to say, you know, we need this kind of tank here and we need that kind of tank there, and then just get quotes on joining them up with piping and a pump to suit. However, water needs to enter tanks in the right plane and at the right speed so the tank contents don't mix. And effectively, a stratified tank can hold as much energy as one twice its size if this is done well. Back to the slide, and Three Ravens. We did a system flexing where we modeled scenarios. How many crash cool processes could we possibly do, Brendan? How many brews could we possibly do? And let's model it assuming the heating is on full and the cooling is on full if we're doing that variation of the project. And the conclusion, basically, for ultimate flexibility was that we need to include the storage system in the PLC so we can tell what's going on at all times. So not the temperature probes up and down the hot liquor tank and the glycol tank. And then we wanted to add more storage. So we actually put in a 29 kilowatt hour phase change material thermal battery, which more than doubled the effective size of the storage in the glycol tank, and we added a coil, a large stainless steel coil in the CLT, and the coil makes the system cool liquor much faster for multiple brew days, and it adds a possibility of ice bank storage for some operating scenarios. So basically, we can pull that temperature right down. And once it's down to 0, we can keep adding cool into that if we want to keep heating out the other end, or if we want to do multiple batches rapidly. So we are getting towards the end here and how things actually stack up. And this, what we see is the price per kilowatt of different size systems from the same supplier delivered to site, 18, 45 and 60 kilowatts. And this was because, yeah, we found it very expensive per kilowatt, and we just thought there was some other energy services on site we wanted to retire, namely some R22 split systems. Okay, so the 3 systems have the same number of components, and the gas cooler, for example, is exactly the same physical size for each. Different specification, same size. And part of the reason for proposing the expansion of 3 Ravens was this reason of cost. And unfortunately, small is expensive. I'm confident costs will reduce in turn, especially as more uptake of these sort of things. But there's always going to be a cost to kilowatt benefit to going larger. So this is a basic business model of the project. One case, which is 18 kilowatts, is just sized for brewing loads, and another for an expanded project, which removes the R22 equipment and runs heating and cooling from the central CO2 plant. Interestingly, if we took this catastrophic scenario of all that Freon equipment degassing and dumping its refrigerant, it would actually be more than the annual emissions from this plant, from the whole brewery. And think of all that wonderful beer that's being made, and the emissions are there for that. But just getting that again from releasing R22 would be a shame. So it would be great if we can actually integrate that as well. The project finances does include an offset for upgrading those HVAC systems with business as usual alternatives. Okay, so in terms of getting these projects over the line, this is very high profile, and industry and government bodies appear to be extremely supportive. There's lots of grants around, and they're helping us to retool industry and come out clean and lean. And every month there appears to be new grant mechanisms springing up. It can be a challenge to get over the line without seriously investigating funding sources, and this can be a key to success. If something only has a 15% return on investment, but you can get finance at 6 or 7%, then it can be cash positive anyway and allow you to do your upgrade. But having an engineer prepare a business case based on a study will facilitate and help this for many of these green finance people. But better to fund it with grants as much as possible and pick up the difference with finance. Measurement and verification methodologies are often overlooked, but can be worth investigating to make white certificates, especially in New South Wales and Vic. Although processing can be quite expensive, up to $10 a white certificate, that still leaves around $30,000 as a bonus 12 months after implementation of a project the size of 3 Ravens in Victoria. There is a bit of a problem due to effective range. You have to be very careful in constructing your measurement and verification models, and there's very little way out of it if you're going to massively increase your production with the upgrade. So it may not be viable for all cases, but worth looking at. Okay, so that's basically about the end of the presentation. But I just want to summarise that there's a lot of craft brewers in Australia, and they're undoubtedly a good thing for humanity. But there is a lot of work to reduce the emissions they produce. We need to cut out the middleman when it comes to heating and cooling. All those chillers make enough heat to run most of your business. If you didn't just blow it off into your brew hall or out your roof. This presentation on our engineering approach has been customized to brewing, but any entities that heat and cool should be able to adapt their processes to doing it. And yeah, we can let's have some questions. Thank you for listening.
Very good. Thank you very much for that, Jon. I think that you really demonstrated the need to look at those energy flows and really almost go back to scratch with that the brewery design and work out where these energy flows are going and what's really required. So yeah, a really good approach there. I think a lot we can all learn from that. So well done. Thank you.
Thank you.
Question here from Cameron Stanley again. 3 Ravens Brewery, how big was that one? Hectolitres, any idea of that one? How many brews they do per day, per week? And in terms of how they use that, that feeds into coordinating the heating and cooling demand.
It's annoying. I anticipated that question, but didn't have my hand on the answer. If we could pull up Brendan, you might be able to answer that. Is Brendan around?
If Brendan's on the call, he may not be able to come through and talk. Maybe you can write that through on the chat. So Brendan, the brewer.
Yeah, it's basically.
Yeah, I'll be able to bring Brendan in as a panelist. There we go. Brendan, you there with us now? Just need to unmute and you're in business. Hey, Brendan, welcome.
Well, hi, how you going? So nominally the brew house is a 12 hectolitre, although we push it to about 18 or 19. We're currently brewing probably 3 times a week, with the plan to move to at least 4 in the near future, and then up to 8 with increased upgrades that we have planned. So I guess a lot of the scope of this project was applying a continuous process to batch brewing, which is where Jon spent a lot of his work figuring out the buffers.
Thanks, Brendan.
Was there another part of that question?
Yeah, how many brews? We got that one, and the size of the brew house. Done.
Excellent.
Apparently 18 hectolitres, but only purchased 12, so that's good. Good value for money there. And moving towards, was 8 brews per week or so that you're heading towards there?
Yeah, actually, the system will do. We've modelled 10 just to be on the safe side for Brendan.
And Brendan, while we've got you there, how's the? So is this being moved into the marketing for 3 Ravens in terms of their CO2 emission credentials and what have you? Is that working?
Yeah, certainly. We plan to. I think as the project rolls out, we've been promoting the solar aspects quite heavily. It's always been a big part of our company philosophy. Brewing being such an energy-intensive process in industry, it's our I guess our responsibility to work on it. So hopefully it's something that we can promote ourselves, but also help others to apply to their own processes. I know it's not something that's used particularly commonly in brewing, so hopefully we can make it work and also help others by sharing that information.
I think we do see potential for what's been done here for other processes as well, other brewing process. So great, thank you. Michael, any comments or questions from yourself?
Yes, I think the important thing besides the CO2 heat pump, I think the important recognition here is the necessity for integrated controls. So because this is not only a heat pump project, not only a brewing project, it is a case of correctly pre-charging the glycol tank and pre-charging the hot water tank and scheduling that. So Jon, maybe you didn't underemphasize that. That is an important part of the success of this project, is actually having that scheduling and the anticipation of the need correctly done. So there is a task ahead to get that dead right. Yeah. Jon, you might want to comment on that.
Yeah. So yeah, well, there's coincidentally at the same time there's a integration of a new PLC system to run the brewing. So it's a very advanced PLC, and it's also going to be able to integrate recipes and brew or complete buy time, so that, you know, Brendan will say, I want, you know, this kind of beer and this kind of beer completed by this date, and then the process will be able to schedule all the activities to make the best use of the energy available, and also hopefully to integrate the solar energy, which is free in the middle of the day, and skip the high peak rate energy at the end of the day. Because we've got these thermal batteries, which will be very valuable. But yeah, there's a lot of analysis involved, it must be said, but it will hopefully pay itself back. Thanks,
Jon. And one final question there for Brendan on the costs of energy as terms of an input for you. Have you got a handle on how much that energy is as in terms of an input cost of your total input costs?
Not off the top of my head. I'm not sure if Nathan in the chat, whether he's listening, he might have some more information. Jon, do you know?
There was a factory cost. I think factory cost of energy was about, was it 6 or 7%? I think it was. We had that as a metric, and that's for a sort of standard industry. That's quite high. I think often entities run on a 2 or 3%, but it's fairly energy intensive, being well over the 5%.
Yeah, quite a band, but quite often we do see that in beverage manufacturing, around 3% for their total costs. Thank you. Jon, Michael, Brendan, thanks very much for joining us today. We'll move on, and I was glad you could answer that cost for energy and what have you, but it does lead us into our next presentation from Bill McGhie at Simble Group. Bill's the energy and climate specialist and product specialist for SimbleSense and measuring and monitoring there. And Bill will get you to share your screen and get ready to take us through solutions for metering and monitoring, specifically for heat pumps. And as the skies open up here in Sydney, I'll have to go on mute before we hear more thunder. Over to you, Bill.
So can everyone see my screen?
Sure can.
Beauty. So I'll try and keep this short to get us back on track. But essentially, some of the points that Jon raised, you know, things like short cycling of chillers that were unknown, different issues that have cropped up will be relevant to the presentation that I'm about to give. So just describing how the work that Simble does, and we're a software as a service provider we provide a energy management and IoT platform that collects data from all sorts of sensors and houses it on one pane of glass. One of the issues that we've found that can be a hurdle with heat pump metering, for instance, and establishing a baseline is the idea that we can't really get a baseline because there's no sub-metering in existence, and gas meters themselves, to put individual gas meters into boilers, into the supply lines is not an expensive exercise. And for the actual pulse reading equipment and communication equipment that you would accompany that with, because you can then reuse it in the post-upgrade process, that money or that investment's not wasted. So you're not throwing out all the equipment that you put in place to establish a baseline. So you can see here just the small graph on the right there that shows the time of use for gas this is just in a house, it's for the UK, and it's just showing the time of use for an existing boiler. This company actually did exactly what you guys are talking about, and basically established ground source heat pumps in the houses, and I'll show you some of the output from that following. But being able to establish the actual volumes of gas usage and when it's used in the existing boilers can give you an idea of the loads that are required and indicate any potentials for peak demand for your heat pumps, and the idea of, you know, the thermal batteries and whatnot could be specified more accurately having this information. So this is a fairly simple sort of thing to install. Essentially, once you've got a gas meter installed that has some sort of pulse output, we can put a pulse reader over the top of that. there's a whole range then of readers that can either use Ethernet, Wi-Fi, 4G, or LoRaWAN to get that information to the cloud, and then we can display it. On a post upgrade, you can include other sensors. So we've got data from temperature sensors, supply and return from heat pumps, and you can see this graph incorporates the energy use for the heat pump with the supply and return temperatures, and then temperatures, the yellow and the pink line down the bottom indicates temperatures at different points in the house. So the idea is that we can incorporate a lot of information from a wide variety of sources in a pretty cost-effective sort of way. This equipment is very flexible. It's industrialised, so that you can run it in commercial situations, even though the information I'm showing here is based on residential. So I'll just go on to the next. So just covering the capabilities. So it doesn't really matter what you're trying to measure. So whether it's energy from electricity, from gas, whether it's water, temperature, solar output, battery performance, all those sorts of things, SimbleSense can store and display that data. So I'll open it to questions there. That's basically all I wanted to cover.
Thanks very much, Bill. And if I do the usual thing when people think about metering, they won't ask first about what is the value this brings. They first ask, how much does it cost? So let's start there like usual.
Yeah. So the cost is based on the extent of the system and which way you go. So for instance, if you want to do, the temperature probes, for instance, to do the heat pump in that, where you can have, I think it's -40 to +250 sensing, you're looking at around $300 for that unit. For a pulse reader, around the $250 mark, depending on whether you're using a LoRaWAN version or something like Sigfox. The gateways can be anything from $300 through to $1,000, depending on how expansive the facility is. So if you've got a particularly large facility, you might be heading up towards one of the more expensive gateways if you're using LoRaWAN. But if it's a reasonably compact facility, going by the size of the roof with the beers written on top, the Dan Andrews roof, then that would be something where the cheaper end of the range would probably cover that. Given that the LoRaWAN coverage, they say in open space, so in a farm, for instance, you can have sensors 15 kilometres away. So its penetration is very good. And you can have, a couple of hundred sensors running through that gateway.
And with this installed, then you can be sure that your new heat pump project is delivering as expected in terms of the overall COP and energy consumption there. And actually watch that, no doubt, over time as well, Bill, to see if there's any sort of fade off in the performance.
That's right. And the client can watch it as well.
Yep. I think you might get a call from Brendan after this one to say, yeah, we want to make sure that what Jon does is right on the money. Perfect. Thanks very much. A question here from Trent Hawkins there. Can you integrate Modbus TCP IP output from a gas meter into Simble or any standard digital output for that matter?
Yeah, so Modbus would require a device like this that basically is a Modbus to LoRa converter. What we'd need is the tables to integrate the gas meter that you're talking about. So we can send the queries, get the Modbus data back and send it to the cloud.
Yep. Good one. And a comment here from Mario, I think supporting your position here, Bill, saying that always good to incorporate metering costs in total overall project. Justifying metering on its own usually proves difficult.
Yeah, and with those certificate claim processes, it's generally essential in those as well.
Yeah, exactly, for that M&B side of things, to prove that we are, you are getting that CO2 reduction or reduction of electricity. So very good. Excellent. Bill, many thanks. Always good to have a metering and monitoring element to whatever we present. It's so essential to moving forward. So thank you very much.
Thank you.
Good. Andrew, just before I forget, Andrew Clark asked a question before for Veronika about the a detailed case study on the brick drying case, but I understand that was no doubt coming. I think I saw, if I saw that correctly, Veronika, on the 6th of July, when you'll have your findings coming from that one there. So just a few months away before we see some more detailed analysis and case study from the brick drying, I imagine. Good. If I may...
Yes.
Yeah, so that's right. We're all waiting for July. You've got us. You'll have us all signed up for July then. Thanks, Veronika, confirming. I'll share my screen. Just we'll go through the final stage and the final wrap up for the where we are with the arena process heating. So yeah, we've been running the program for a couple of years now, and over the time we've done 20 or so feasibility studies and 7 feasibility studies, one of which there for 3 Ravens. And I thought it would be a good time to give a summary of how things are, the results for those feasibility studies. And then after that, I'll give you a quick demonstration of the calculation tool, which has been developed using the knowledge coming from these feasibility studies, pre-feasibility studies as well. So a quick summary of some key learnings over the last couple of years when going after a heat pump project. Heat recovery first. Energy efficiency is the first fuel, so absolutely do that. You do need to have this integrated design and have some skills in something like a pinch analysis, or at least be very good with a mass and energy balance and understand energy flows. We did do a couple of studies on covered anaerobic lagoons, CALs, and we certainly saw that the return on investment is a fair bit lower than what we saw for most of the heat pumps, and in some cases, very specific cases like in a piggery, we see very good return on investment, but in sort of a generic wastewater for a food and beverage plant, not so much. We saw some pretty reasonable return on investments for solar thermal, and very good opportunities for that to provide heating above 100 degrees, and certainly provide that steam cooking duties where there is so much of that in food and beverage in Australia. We certainly saw the very good return on investment there for heat pumps, but there's a lot of different factors that need to be ticked off to make sure you get that good return on investment. Probably a little bit less flexible in terms of its performance versus a few other alternatives. And yeah, absolutely, better metering and monitoring needed for heat systems to allow these informed decisions. We did see some cases where there wasn't the data available, and a few more Simble type systems in place would have helped. We saw that the success factor is very much that ratio of electricity to gas price, or having low on-site renewable energy with those solar panels. That helped a lot. Equip process knowledge so that you could understand the heat flows and understand how to integrate any sort of new system was essential as well. A heat lift to say less than roughly 50 degrees, and we saw that a little bit with Veronika's presentation today. As you get up towards 60 degrees, that COP starts coming down below 3 and starts affecting the return on investment a fair bit. But with a heat lift below 50, we saw very good COPs and very good return on investment consequently. Equipment utilization, we certainly saw cases where if the heat pump was only operating for less than, say, let's call it 2,000 or 1,000 hours per year, that was greatly affecting the return on investment because of the high capital costs there. And a thermal battery, that some sort of availability, if that was in place already, we definitely saw very good return on investment. And that being just, say, whether that's just being a large hot water tank that was there or in place already, that certainly helped things. The final success factor was the availability of electrical supply. We did see some cases where the local substation needed to be upgraded to allow for the heat pump installation, and that certainly made the economics rather poor as well. So the phase 1 studies, this was largely done through 2019, and here's a quick summary from those that have joined earlier webinars would be familiar with this. And you'll see there's a range of different applications, somewhat focused on food and beverage there. So a little bit of steel and other, but mainly food and beverage. And most of the solutions we looked at there were for heat pumps. The outcomes for most of those are that they have a good return on investment. We're talking internal rates of return above 20%, and most of the time they're waiting for FID, or they've been put into sort of a strategic capital works program. And you'll see that is the case for most of the studies that were done there. A few cases where we've had, you might need a site champion. The project has sort of fallen off the radar a little bit, and the project needs a site champion to push that further forward. A few cases where it was a smaller heat load and therefore lower return on investment as well. And certainly the return on investments I quote there, like an internal rate of return above 20, that excludes anything that would come from potential government grants and what have you, which would dramatically improve the return on investment for nearly all of these. Phase 2, and these were the studies largely done through 2020. These again were quite focused on food and beverage industry through most of those, and certainly that was by design, where focus was on that temperature range of say 65 to 95 degrees, and so that's why we ended up with these sorts of applications. Again, largely all good return on investment if we meet those criteria described before. With a couple of those I've highlighted in green are proceeding to FID and looking for grant applications. Of course, one of those today from 3 Ravens. Another one, as we presented last year, was from Hardwick Meats, and they are both, looks like they'll be both heading towards installing heat pumps and reducing their emissions. So a quick summary there, 100% of sites, if you had low temperature needs, call it around 65 degrees, maybe up to 70, 75, and you had a heat demand greater than 200 kilowatts with high utilization, if those 3 factors are sort of met, you'll definitely have a good return on investment that sees it stand alone without having any government subsidies. 65% of the sites that have had a study done all have a good return on investment, and just waiting for that FID to go together, and most of them are in a capital works program. A few of them, 20% or so, made difficult due to lack of data and a little bit of uncertainty there. And 20% of them also were relating to smaller heating opportunities and made things a little bit difficult with the return on investment. And then finally, there was about 5%. There's just one site that needs to do heat recovery before looking at alternatives. So where to next with the ARENA programs? ARENA, as you may be following, are changing their remit to look at much more of not just renewable energy, but for energy efficiency as well. And for those of you that joined there's a webinar update this week where they're planning to roll out a new, I think it was $25 million program for energy efficiency studies. It looks like focused mainly on large energy users. But that's part of what ARENA will be focused on. So this particular heat pump study and program will be coming towards an end, a closure in the next 4 or 5 months. However, New South Wales DPI are looking to do more with what's been done with ARENA, and they are looking to apply the learnings from this ARENA project and see how they can implement that and encourage further adoption of heat pumps and non-fossil fuel process heating in New South Wales. We also expect the likes of Victoria to follow this as well and start doing more of a specific local program. And then hopefully other states will follow as well. Right now within DPI, A2EP is running a very small pilot program to test a screening method and a sizing tool, which I'll show you in a moment, in preparation for possibly a larger series of funded studies. So right now we're looking at doing a quick screening test with some different sites, and those are hotel, hospitals, and a few different manufacturers, things like dairy, paper, bricks, chemicals. If you want to be involved, please give an email to Simon Ray at A2EP, the email's there. And Simon will get you on the list. And if you don't make this small pilot screening, we'll certainly make sure there's some consideration for future process heating studies as well. So again, please just email Simon if you're interested there. So moving on to our sizing tool demonstration now. Just check, we've got 5 minutes or so to go through that. Let's see how I go changing screens and see if that comes up for everybody there. Possibly not. Let me see if this one comes up. And hopefully that's come up for everybody there. It looks like it's sharing correctly, so hopefully that's there. If there's any problems, hopefully someone will tell me. This is the tool that we've developed in collaboration with pitt+sherry and SmartConsult. We had sponsorship from Arena, as well as AMPC and Mayakawa, and many thanks to those organisations for their support. But what we've done is taken a lot of the key learnings from these process study feasibility studies and put them into this quick calculator. And this will allow people to do a quick simulation and see in a sort of a live environment how changes to process data or process conditions affects the viability of a heat pump project. So if you'll indulge me, I'll just quickly go through how the system works. And you start off by entering the fuel cost here. I've got $16 per gigajoule. I think we quite often see around about 14. We'll put it in at 14. I've entered in the number of process hours per annum. At the moment it's 6,000. Let's say you're maybe just working Monday to Friday. Maybe it's closer to 4,500. Electricity costs there, I think I'm hearing rates of 7 cents a kilowatt hour if you're just looking at solar PV, but why don't we just say it's at 0.1 for kilowatt hour. In this case, you can choose your heat source, whether you're taking the heat from the air, groundwater, or water. For this first one, we'll just do a water simulation. And you can enter the location, and that will automatically help you out with the air temperatures if you're using air as the heat source. Then you move on to sizing of the actual equipment, and you're entering in let's say the size of the heat that you require is 500 kilowatts, and you require heating for your sterilization water at say 82 degrees. This may be returning from a factory or from freshwater feed. Let's say that's coming in at 60 degrees. And then you are, let's assume you're using hot water from your refrigeration plant at, let's call that 25 degrees. The heating, this cooling is, let's say that is useful, and we'll take that down to 15 degrees. Immediately that will give you a result here, and hopefully you see that in the bottom left. It gives you an approximate capital cost there. So for ammonia heat pump solution for this, we've got 670,000 and 865 for a CO2. Now this is again just using a lot of data that we've gained over the last couple of years. We've been maybe a little bit optimistic on the capital because it is a big range. We saw often that the cost of the overall installed project was about 1.3 to 1.5 times the cost of the heat pump equipment, but at other times it was say 2.5 times. So it does vary a lot, but we've been a little bit optimistic there. And this also gives you an approximate operating saving there as well. With that, we'll give you a net savings of from your energy and a rough payback there. So that gives you a very quick indication. From there, you can look at different sizes of the heat pump, or you can allow for, if you have a peak requirement of a CIP load in the morning, and you say, well, in the mornings we've got 700 kilowatt load, and that goes for 1 hour. The system will also quickly do a back of the envelope calculation for a thermal storage for you as well, and put that into the model. So that way you don't need to size that heat pump for the same size that you have for the current steam boiler. So that's the very quick calculation. You can also take this further, a more detailed calculation by entering in your current heating system efficiency. And say if you've got a steam system, it can operate anywhere between say 30% and 70. Haven't seen anything much better than a 70% for an overall system, but we've got 50 there at the moment. You can put in your other operating costs for the system, and maybe that's a boiler maintenance, annual maintenance of $10,000 per year. The current cost of the boiler, and let's say it's an $80,000 for 500 kilowatts. It's probably closer to $60,000 for that. Well, not even that much. That's 60 for now, though, for that boiler. And let's say you've got 10 years life on the boiler, an 8% discount rate, and let's say 50% of the energy is coming from solar, and that'll do another calculation there for you as well with a bit more advanced calc. So they'll levelize cost of heating in terms of dollars per kilowatt hour, the storage that you're available, and the NPV over 10 years. So that's the tool very quickly. I'll come off, we'll stop sharing that one and see if there's any questions. I can keep that sharing. If there's any questions, feel free to put that out. James Taylor, yes, the spreadsheet is now finally available. There's been some extensive testing. There's no bug-free guarantee, but it is now available. If you give me an email, I'll give you that email address in a second. I'll shoot that through to you, James, but I'll note that you've put a request in, and I'll put that out for you. We would like to put that onto the website, but we need to do some changes to get that up there on the website. And actually looking for some further sponsorship to take that to the next level of integration to the website and ease of use as well. Good. Chris, did I see you have a question there? Maybe you'd like to type something in there for me. Nope, nothing further. Okay, very good. So if there's no further questions on that one, we can wrap things up. There's my email address. If you'd like a copy of that one, just shoot me an email and I'll be sure to send that off to you. Good. So thank you all for joining today, and thank you very much for our speakers. Dr. Veronika Wilk, thank you very much joining from the Austrian Institute of Technology. Jon and Michael, and as well as Brendan from the 3 Ravens case story, thank you so much. And Bill McGhie from Simble, thank you very much to our speakers. Coming up for you, we have a webinar with Tennant Reid from AIG and giving us his forecast on energy pricing and all energy market matters. We'll also coming up in April then, again with AIG, we're talking about compressed air. The report that we've done for New South Wales DPI is now complete and is ready for issuing, and we'd like to share with you the fantastic results we saw from that one. Coming up then, and then in May, we'll be doing a webinar in conjunction with Bioenergy Australia, looking at biomass and biogas. And then through June, we're going to do a session on thermal batteries and facility integration, and that will largely build on the work that we've talked about today. Overlaying that, we'll have a series of presentations and webinars from Race for 2030, the Energy Productivity Cooperative Research Centre that we're working with very closely, and we'll be keen to bring you updates from there as well. Before I close off, it looks like we've got a couple of comments in the chat there. Thank you very much, Laura, adding in the links there to register for the event with Tennant Reid coming up. And also then, looks like you've got both put in there twice for that one. Oh, and for the panelists as well. Thanks for putting that in, Laura. But otherwise, thank you all for joining us today. A pleasure to have you with us. We'll see you again in just a week or so's time. If you do need more from us in the meantime, plenty of activity you'll expect from A2EP over LinkedIn, and feel free to follow us there, and you'll see lots of updates on things like new grants and things available. So please feel free to join us on LinkedIn. Otherwise, thank you all for joining today, and I wish you all a pleasant afternoon or a very pleasant day. Thank you.